camera lens math. I've decided to just talk a little bit about this problem I had because I put some of the math online. Some people have Sam Friedman asked about it, or asked about the math, and I figured I'd take this opportunity to talk about the problem so I could work through it again myself to kind of double check my own rationale and to play around with the video on my camera, which I haven't done a whole lot. I'm still trying to learn. So, the issue is, this came to me from an engineer. An engineer has hired me to figure out what is the best lens to put on his specialty infrared-only scientific camera to take an image of a 2 meter by 1 meter solar panel. And he's going to have a whole slew of these things. He's going to have 50 panels, and this might be the first shipment of several 50 panel shipments. So he's trying to determine the best way to do this. Because right now he has the camera, and it's an oddball, scientific, it's not a standard commercial camera. He's got this camera, and and it takes Nikon lenses, and he's got a 28mm Nikon prime lens on it. And to capture a 2 meter tall, roughly 6 foot tall panel, he's got to be 12 feet away, which doesn't make too much sense. And part of the problem is that to do that, in addition to having to be 12 feet away to capture this, he also has to build sort of a tent around it. I'm not quite sure on this aspect of it. It's not really my job. But he has to. It's just a pain. He's got to, being farther away, he's got to build this protective barrier around both the camera and the eventual panel. And so the goal is to shorten the distance between the camera and the panel while still being able to capture the entirety of the panel in one shot without, introducing too much distortion from like a fisheye lens. Now theoretically we might be able to use a fisheye lens which would capture almost everything from way up close, because we're never going to be close enough that the minimum focusing distance will be an issue. The closest we're shooting for is a meter away. Right now he is 12 feet away, which is 3.65 meters away, which is really far. So if we can shorten that distance to a meter or less, that's golden. But, I'll jump into that in a second. So the real obstacles here are, one, I don't have this camera in my hands. I don't know how it operates, and it's an oddball camera. Two, in addition to finding the right lens, I've got to find a lens that I can fit a specialty filter on. A filter that takes out everything except for the infrared spectrum, which is actually a standard commercial product. You can buy those for all kinds of camera sizes, but, well, the filter might be an issue. We'll run into that in a little while down the road. And so that's all I've got to work with. I've got a camera, I've got a lens, some little bit of data, and I've got to hit these points. Let's get it as close as we can. So I started digging into this and saying, okay, what do I know? And how do I go about doing this? Well, the only data points I have is how far away it is, how big my target is, and the angle of view, that a lens can see, So a very, very wide lens, like a fisheye lens, can see everything. A wider lens might be able to see this much. A really long telephoto lens is only going to be able to see this much, really far away. Okay, so we want a lens that can see a lot. And so let's start looking at specs for that. So I hopped onto the internet, I started looking up lenses, and they start giving me all these angles. It's called the angle of view. And I'm like, okay. And then I start looking at them, and I go, wait, these don't make any sense. And that's where I realized they're always listed as the diagonal angle of view, which is totally useless for this purpose. So here's the way to think about it. Anytime you're buying a monitor or a TV, they never say it's 19 inches wide and mean 19 inches from here to here, because they could much happier to say it's 21 inches wide from corner the corner, this diagonal, it's just a marketing pain in the ass. So I looked at all this and I was like, great, I can't find this data anywhere. It's certainly not on the spec sheets from the companies. Thankfully, a million times over, Wikipedia. Going to the Wikipedia page, it gave a standard breakdown of angles of views for standard millimeter focal length lenses. So it had, a whole slew on there. Anything from 0 up to 200. And then, in addition to the diagonal angle of view, it also broke down the vertical angle of view and the horizontal angle of view, which is like, yes! Because what we really want here is the horizontal angle of view. How wide can the camera see from on its widest, from side to side, like that. So this would be the horizontal angle of view, this would be the vertical angle of view, and this would be the diagonal angle of view. Now if I'm trying to capture a 2 meter by 1 meter board, the only one I really care about is this 2 meter distance, which would fall into the horizontal angle of view. So now I've got that data. It's like, great, okay, I've got the angles of view, I know which ones I need. Well, I might be jumping ahead there. But I know how, thanks to this chart, how the focal length will relate to the angle of view, for the angle of view that I care about. Again, the horizontal. So that's the relationship I got right now. I can figure out that. Now, I got to figure out, well, if I've got this angle of view, how far away does the camera have to be to hit 2 meters wide in its view frame? So, because I haven't used math in God knows how long, I completely forgotten all my trigonometry. So again, Wikipedia. Looking at this, it's a series of triangles. It's really just two, If I've got a triangle coming out of the camera, so, here's the camera, I've got the angle of view coming out, and here's the panel I'm going to hit. Well, if I look at this, I'm just going to split that triangle in half. Now I've got a right angle triangle. Right angle? Yes. Right angle triangle. It's going to hit the panel at a right angle, and then here's half the panel, and then I've got half of the viewing angle that I want. So, thankfully again, Wikipedia, a little refresher on math, a little trigonometry, I'm looking at the tangent, which is the opposite over the adjacent. Yeah. I don't know, I've gotten written out. I did the math, I can't remember everything, or anything. So I did a little bit of trigonometry, and I was able to determine a relationship between, I could find out how the angle, the viewing angle, relates to the distance. And I punched in a couple of numbers, and I came up with a rough chart. I suppose you could have graphed it, but I haven't done that in forever. I don't know where my graphic calculator is. And I found that what I'm really looking for to get, let me see if I have this right, to get 1 meter away is I need a lens with a viewing angle, or an angle of view, of about 90 degrees, which should fall between a focal length, according to this chart that I found on Wikipedia that gives horizontal angles of view versus focal length, between 16 and 20 millimeters. Actually, yeah, that's accurate. Between 16 and 20 millimeters. Well, that's great. You can find those. You can find a 16 millimeter lens. You can find an 18 millimeter lens. Even a 20, We'll get a 20 and just back it up to, I think I worked out for a 20 millimeter lens, you are just over a meter away. So that's great. That's 3 feet. We've cut down from 12 feet to 3 feet. That's like a 75. That's awesome. That's great. And now with a standard camera, if this camera was a 5D Mark II, like I'm recording on right now, it's like, we're done. Go buy that camera, go buy that lens with a 16 millimeter viewing angle, and you're set. I'll invoice you next week. Like, that would have been great. Of course, that's not how it works out. Because here's the snaggly thing. this is not a standard camera. This is a very non-standard camera. And the only data point that I have about it right now, because I looked online, the camera's made by a German company, and their spec sheets are pretty sparse. All I could find out was the sensor size inside of the camera. That's the only thing I have to go on. And that I can accept Nikon lenses. So I started to look at the one piece of data I have, which is from the engineer himself, saying that when he puts a 28mm focal length prime Nikon lens on the camera itself, he has to be 3.65 meters away, or in other words, 12 feet away to hit the 2-meter wide board. That doesn't make any sense. According to my own math, I think I might not have it here, but a 28mm lens, you should be able to get half that distance away. You should be able to hit that from 6 feet away, not 12. So what's going on there? So, thought about it, looked into it a little bit. The only bit of information I can find online, again, is that this specialty German infrared camera has a sensor in it that is significantly smaller than a full frame sensor. Either that or the camera's overheating. I don't think it is. So I was talking about sensor sizes. And I was saying that what I know about sensor sizes right now is that commercial cameras typically come in one of two sizes for the sensor. Now the sensor is the digital chip behind the lens that actually captures the image. And in a film camera, it's actually film. It's a 35mm film. But of course, in digital cameras, they don't have film. Instead, they have the chip. Now, this chip typically comes in, again, two sizes for commercial cameras. For standard digital photography cameras, like the one I'm looking at right now. They come in a large size, with called a full frame, which is typically 35 or 36mm by 24mm, just like film. And then they come in a crop size, which is 24mm by 16mm, thereabouts. Okay. Now, this has a lot of impact on a number of factors, but the thing we're concerned about for this particular problem is how the change in sensor size changes the effective focal length of the lens. So, for example, if you have the full frame sensor, the big sensor, the 36 by 24 sensor, and you take a 50mm lens on it, and you put it on, it just acts like a 50mm lens. It's totally normal. Now, if you take that same lens off, and then you take the camera with the crop sensor on it, the smaller sensor, the 36 by 24, no, I'm sorry, the 24 by 16mm sensor, just smaller, and put that 50mm lens on it, it no longer acts like a 50mm lens. Now, it acts like a 75mm lens. Yeah, so that change is what they refer to. The quick math they do is the crop factor is 1.5 times. So if you want to go just to estimate a lens going from a full frame to a crop frame, you multiply the focal length by 1.5. It's typically 1.5, 1.6. So if I got a 20mm lens on a full frame, and I'm going to put it on a crop frame, now it's going to act like 1.5 times that. It's going to act like a 30mm lens, if I'm doing that right, which I really hope I am. That should be pretty easy. Okay, so I looked at the data that my engineer had given me based on his camera and the focal length of the lens he put on it, a 28mm lens. And then also I found on the website for the camera manufacturer that their sensor is even smaller than the crop sensor. So it's even smaller. It's 18mm by 13.5mm. So you think about it, if on a big full frame sensor I got 50mm, and then if I take it to the crop sensor, and all of a sudden 75 millimeters, and that's a much, it's a smaller sensor. If I go to an even smaller sensor, well, it's got to be an even longer effective focal length, which sucks. It sucks for this problem, but that there's no getting around that. That might just be the case. So I ran a little bit of math. I looked at the distance away he is to hit, roughly 12 feet, 3.65 meters, and to hit 2 meters wide, the panel. Well, that means effectively it all shakes out using the angle of view and the tables that I talked about earlier, that instead of operating like a 28 millimeter lens, it's now operating like a 70 millimeter lens, which means we've got a crop factor here of roughly 2.5. We got this major crop factor. And I can't remember if I mentioned this on the first clip, but I'm playing a little fast and loose with the numbers, rounding things off, because I'm not going down to the millimeter. I just need things, closer, roughly closer, Yeah, I'm not doing hard engineering here. So that means I've got a crop factor of 2.5 on this camera, which sucks. Which means that even if I've only got a handful of solutions right now. I can find a really wide open fisheye lens, or I can find a more reasonable 20 millimeter lens. Now, I looked at a really wide lens, just prior to fisheye, not quite as wide open as a fisheye, 14 millimeter lens. Now, a 14 millimeter lens is going to act like a 35 millimeter lens due to this smaller sensor, due to this crop factor, this 2.5 times crop factor. Now, a 35 millimeter lens, or effectively a 35 millimeter lens, is still going to have a viewing angle that you can get 2 meters away and see the whole panel, as opposed to 3.65 meters away. Which means that you can get, almost half the distance, which is pretty good. That's not bad. We're talking about 6 feet away instead of 12. That's not bad. It's a little bit better. Or we could have a 20 millimeter lens, and that's going to get you 2.75 meters away, or 2.77 meters away. So you're going to get 9 feet away instead of 12. I'm like, all right, that'll work. Now I'm really pushing hard for this 14 millimeter almost fisheye lens, because I think it's really going to do the trick. And if the problem was done there, I would just turn to my engineer and say, buy the 14 millimeter lens. Yeah, it's $370, I believe. Just go for it. Now, here's the other wrinkle. On really wide lenses, where the focal length is very small, anything pretty much under 20 millimeters, if you actually physically look at the lens, look at the end of the lens, the glass comes out. It's convex, I believe. Well, a deal breaker for this problem is that we have to put an infrared only filter over the lens. It's totally useless to my engineer unless I have that filter in place. Well, with a convex lens like that, there's no way to fit a flat filter over it. No way. Which means you got to go for a 20 millimeter lens, because they're still flat on the front. You can fit a filter over it. Bummer, all right? So I started digging a little bit more. It's like, okay, somebody's got to run into this problem before. So right now we've got one solid solution, 20 millimeter lens, but it's imperfect. I'm not happy with that. I want to get closer. And that's going to cost about $300 used. But it only gets us maybe a meter closer, okay? So 14 millimeter lens is going to get us significantly closer. Yeah, almost 2 meters. But we've got this filter problem. So I started digging into this. I was like, how can we fit a filter over this? Now, it turns out that there is a filter holder for this specific 14 millimeter lens that I'm looking at, but it's only specially ordered over in Europe. And even if I were to get it, I'd still need to get the filter. Now typically, these filters come in standard sizes that you just screw over the end of the lens cap. Here's the lens and you just screw it on right here. But, of course, because this is such a wide angle lens, the filter holder actually comes out and it has to hold a big square. Now you can buy this filter material outside of the fitted lens. Normally they come in these like little fitted filters like this that I was talking about, you screw on. But you can just buy the material. But the only size available for it like that is 3 by 3 inches, which is not large enough for this large filter holder. It's like, okay, damn it. So that's not going to work. Started digging some more. Turns out that the people who most often use these kind of wide angle lenses regularly with filters are people that use them underwater. Underwater photography requires a lot of filters for, I assume, what are they called? Polarization filters and things like that to bring out, to negate the effects of reflection in water. So they found out a couple of cool workarounds. Instead of putting the filter on the front of the lens, they found a way to fit it on the back of the lens. Now some lenses have these, have actually a built-in little slot that you put these in. They tend to be very expensive. They tend to start at about $1,200, $1,100. Meanwhile, the 20mm lens is like $200-$300, so it's not really cost effective. But some of these guys have found a do-it-yourself, a DIY hacker way of doing it. Is that they buy the filter material, they cut it themselves, and they very carefully attach it to the back of the lens before inserting it into the camera. So the light is still going through the filter, it's now just going through the filter at the back of the lens instead of the front. So I started looking at this and I was like, this might work. Now, the only other hiccup that I can't check on myself, and I'm hoping is accurate, or hoping that it works out this way, is that if we're looking at this lens, the front and the back of this 14mm lens, it's convex on the front, so I can't fit a filter over here. I'm really hoping that it's not convex on the back, or at least that there's enough of an overhang in the casing that you can slap a filter material very carefully without touching the actual optics on the inside, so it clears it. Let's hope that's the case. I think if that's the case, it will solve the problem, and the lens itself costs, what did I say, $370? I believe it's $370, and then the material that will cut out this filter material, this infrared filter material, is $85. So that's, what, $455? That's a viable solution. So I took this to my engineer and I said, you can get. Alright, I'm tired of this damn thing cutting me off. I don't know how to really use it yet. But in any case, that was the best solution that I found. Material on the back of the 14mm lens. Took that to my engineer. He said, how about that 20mm lens? How about you go get that? So I was like, alright, great, thanks. But I'm going to keep working on them. I think we're going to get the 14mm lens eventually. And so, thanks for listening. If you have listened to this, I'm sorry it's a very long, boring discussion, or one-way discussion. But hopefully you learned something important, or something at least a little bit useful regarding focal length or angle of view or camera size or sensor size or something along those lines. So big thanks from me, James Rand of jamesrand.com, and thanks.